Good morning, everyone. I'm Hadil Hantour, a computer systems and network engineer at University of Science and Technology, wearable. I'm honored to be presenting my project called IoT-HealthGuard, real-time monitoring IoT-based healthcare system at the Off-Road conference. Our presentation will cover four main points. First, we'll introduce the problem and give you the background. Then, we'll walk you through our conceptual study, followed by the implementation and analysis of the results. Finally, we'll conclude with some future works. The Internet of Things refers to a global network of interconnected objects that communicate with each other over the Internet. These objects can include buildings, vehicles, machines, sensors, and various devices. They can be used across various fields, including home automation, transportation, healthcare, industry, and agriculture. The transportation sector has led to the development of a specialized extension of the Internet of Things, known as the Internet of Vehicles. This encompasses various types of vehicles, including personal cars, emergency vehicles, public transport, and security vehicles. They are equipped with communication systems that enable them to interact with other vehicles, sensors, infrastructure, and cloud servers. However, despite this advancement, significant challenges remain, especially in the fields of healthcare and road safety. For instance, the number of people suffering from cardiovascular disease and diabetes is continuously rising, which in turn increases related deaths. A major factor contributing to this issue is the limitations of traditional monitoring devices, which often lack continuous tracking capabilities. As a result, patients may not detect critical changes in their health, such as impending heart attacks or fluctuation in blood sugar levels, until it's too late. Furthermore, road accidents contribute to the number of fatalities. For example, in Algeria, the National Gendarmerie reported 63 deaths, 263 injuries from 165 road accidents during the first week of July 2024. Given these challenges, we face a critical question. How can we leverage the convergence of the Internet of Things and the Internet of Vehicles to develop a real-time health monitoring system? To address this problem, we propose several integrated solutions. First, we recommend using wearable real-time measurement devices to continuously monitor individuals' vital signs, providing a more proactive approach compared to traditional methods. Additionally, equipping vehicles with sensors will help detect accidents and enhance road safety. Furthermore, using location systems will enable precise identification of incident sites and ensure prompt deployment of ambulances. This new healthcare system based on the Internet of Things is called IoT-HealthGuard, specially designed for drivers and pedestrians with diabetes and cardiovascular disease. The system aims to detect discomfort related to these conditions and identify road accidents. It then provides timely medical assistance by coordinating the prompt deployment of ambulances. Our system integrates with three types of vehicles: ordinary vehicles, safety vehicles, and safety professional vehicles that are pre-registered with the system and offer first aid while waiting for the arrival of safety vehicles. All these vehicles are equipped with an onboard unit, an autopilot system, an accident detection system, a GPS, a Bluetooth, and a 5G network cards. Smartphones equipped with GPS and a Bluetooth and 5G network card. Medical watches equipped with a Bluetooth network card and heart rate and blood pressure sensors. Continuous glucose monitoring devices equipped with a Bluetooth network card and a blood glucose sensor inserted under the skin and placed on the arm. The cloud host server, which represents a centralized IT system containing databases required to store and manage all the critical information needed for the system's operation. Base stations or GNODEs, responsible for efficient resource management, and finally the emergency center, which represents a hospital or clinic. Here's the complete architecture of the system components. The communication technologies used are 5G cellular network, and the Bluetooth network. Our system is organized into three subsystems: the information gathering subsystem, the anomaly detection subsystem, and the message generation and routing subsystem. The information gathering subsystem comprises two types of collection devices: medical watch that measures heart rate and blood pressure, and continuous blood glucose monitoring device that tracks blood glucose levels. For drivers, data are collected by these devices is transmitted via Bluetooth to the vehicle's onboard unit, while for the pedestrians, the data is sent directly to their smartphones. The anomaly detection subsystem is based on two detection methods. The first analyzes and processes the collected data received by the smartphone and the vehicle. By making comparisons with predefined reference intervals, an anomaly is detected if measurements fall outside normal ranges. The second method detects road accidents using impact sensors. Finally, the message generating and routing subsystem, which is responsible for generating and routing messages of various types to respond to emergency situations. In case of emergency, there are two important tasks to perform: alerting the surrounding area and searching for a safety vehicle or safety professional vehicle. The alerting process varies depending on the detection scenario. There are three scenarios. The first, when an anomaly is detected by a pedestrian smartphone, the system triggers both an audible and vibrating notification to attract the pedestrian's attention immediately. When an anomaly is detected by a vehicle's onboard unit, the system first activates safety measures, including automatic parking, to minimize risk and prevent further accidents. Additionally, it sends alert messages to neighboring vehicles traveling in the same direction to warn them of the potential danger, ensuring that other drivers are aware and can take necessary precautions. Finally, when a road accident is detected by a vehicle's onboard unit, the system activates safety measures including hazard lights and airbags to protect occupants and alert other drivers. Additionally, it sends alert messages to the surrounding area, similar to the previous scenario. Once the alerting procedures are in place, the next crucial step is to ensure that appropriate assistance is swiftly located. This brings us to the searching algorithm, which is designed to efficiently find and deploy the nearest available safety vehicle and safety professional vehicle. First, all safety vehicles and safety professional vehicles should regularly transmit their positions and speeds to the server using an update position message. This continuous update provides the server with a real-time view of the availability and the proximity of each vehicle, enabling efficient and timely coordination during emergencies. The search process begins as soon as an accident is detected. An emergency message is generated and sent to the server. Upon receiving this message, the server confirms it with an emergency. The server then attempts to select an available safety vehicle or safety professional vehicle based on their availability and proximity to the incident location. If no SV or no SPV is available at the moment, the search request is placed on hold until suitable vehicles become available. For all available SV and SPVs, the server calculates the estimated arrival times using the provided formula. This calculation helps determine which SV and SPV are nearest to the incident's location. The server selects the nearest vehicles to ensure the quickest response time. Next, the server compares the arrival times of the selected SVs and SPVs to determine which can reach the incident site the fastest. It only selects an SV if its arrival time is strictly less than that of the SPV. Otherwise, it selects both, as shown in the example. The server then sends an assignment message to the selected vehicles, directing them to the incident location. Upon receiving this message, the vehicles confirms it with an assignment. The server responds with a medical record message containing the patient's specific medical information. It also sends an update state message to the patient to inform him of the current state of his request. When SPV arrives at the incident site, it sends an arrive message to the server. The server confirms it with an arrive. The same process applies when SV arrives. The server concludes the searching process. Now, let's dive into the implementation details of our system. We use the Omnet++ simulator, integrating several components, iNet, Vines, and SIMO 5G to model the 5G network within a vehicular context, Sumo for road mapping and traffic simulation, and Trace interface to facilitate communication between Omnet++ and Sumo. To concretely demonstrate the effectiveness of our system, we varied several simulation scenarios using the illustrated parameters. In the first simulation scenario, as shown, the arrival times of the safety professional vehicles are shorter compared to those of safety vehicles. This highlights the crucial role of integrating safety professionals into the system to ensure rapid and efficient intervention while waiting for safety vehicles to arrive. The second simulation scenario demonstrates that the average arrival times of safety vehicles departing from various locations are shorter compared to those departing from the same location as road traffic increases. This finding confirms that distributing safety vehicles across different locations is much more effective than centralizing them in a single location such as a hospital. In the third simulation scenario, we observed that increasing the update period reduces the number of packets transmitted but also decreases the data accuracy. This underscores the need for a balance between the update frequency and the data accuracy. We choose an update period of 0.1 seconds to ensure high accuracy, which is crucial for the precise positioning of safety vehicles and safety professional vehicles. The fourth and the last simulation scenario showed that the expected arrival times of safety vehicles remain unaffected by road traffic levels compared to the actual arrival times. This is because our system selects the shortest paths without considering current traffic conditions. In conclusion, our IoT-HealthGuard system offers a robust solution for timely and efficient emergency responses. We believe this system can greatly enhance both healthcare and road safety, paving the way for future innovations in these critical areas. Our ongoing research will focus on extending the system by integrating for computing technology with a hierarchy of servers, including a global server and local servers, expanding the detection procedure to include other anomalies, and to use road traffic management services to improve the management of safety vehicles assignments. Here are some bibliography used, and thank you for your attention.